Okay, what we're going to do now is learn to draw a graph. So firstly, you'll probably have a sheet of paper like this. You're going to have a table of results, and you're going to have the X in the left-hand column and the Y in the right-hand column. Independent versus dependent. So you're going to put the independent on the X-axis, and you're going to put the dependent on the Y-axis. But firstly, you've got to decide which way round you want it to go. So what you normally do is, say you've got the dependent, and that's got a really huge range of measurements, so it goes from maybe 0 to 1,000. But the independent, maybe you've only tested 0 to 10. So you would take the smallest amount, and you would put that on the smallest side, the right way up. You would put that on the smallest side. Then you would take the one with the highest range of values, and you would put that on the longest side. Now, getting the scale right is really tricky, but you're going to aim for things that are not divisible by 3. So if I was going up to 10, I wouldn't go 0, 3, 6, 9, and then a little bit more, which would be my 10. I would make sure, if I had 0 to 10 here, that I would do it in things that were evenly spaced. That's because there are an even number of little blocks in each big block. In each big block, there are 10 little blocks. So if I divide 2 by 10, I get 0.2. And that's quite nice to work with, because I can say, well, 3 blocks is 0.6. But then if I said, this big block is 3, every little block is 0.3. And that's not as easy to work with. But you're going to try and fit your scale so it goes over the entire graph. Now, you want to make sure that you get the exact points. So what I do is I take 2 rulers and say I'm looking for mass 70 and a volume of 3. I'm going to put my ruler up where 3 is on the volume, and I'll put another ruler where 70 is. Where those 2 meet, they cross, that's where I'll put my cross. So I put my point right there. And then I would do that for all the points, and then I would make sure when I've got a building up of all the points that I would put one of the rulers back on and draw my line of best fit. 1 point, the line of best fit does not have to go through the origin. You go with your points. If the points go from here, that's where the line of best fit goes. Don't go last point through to the origin. It doesn't work like that. Then, the straight line graph, what we're going to do if we have a straight line graph is we can use this to find the gradient. So we're going to do gradient equals rise over, you might say rise over run, but rise over steps, the same thing. So I'll pick 2 points. Now those 2 points, they don't have to be the data points, they must be on the line. If it happens that data points like these are on the line, I can use them. If the data points are away from the line, I still have to use points on the line. Otherwise, I'm not taking the gradient of the line. So here I do rise over run. So the difference between these 2 on the y-axis is 6. The difference between those 2 same points on the x-axis is 3. So I get my rise over my run, which is 6 over 3, which would be 2. And then I would put the units on those as well. So it's 2. This is your checklist when you've done your graph. So make sure it's an appropriate scale. It should fill the sheet. Drawn with a ruler. The x-axis labeled x and y. Independent variable here, dependent variable here with your labels. Do they have units? They should have units in brackets after them. Do they have a title? You can underline the title. It doesn't really matter. Correct values put in. I will check the values when I check your graphs to make sure you put them in the right place. General presentation, if you put in a graph, I want to make sure that it's pretty. It looks good. That is what you want to use. Use this video when you're going over it. Right, as a special treat, we're going to go over some amazing physics. This, as everybody knows, is a black hole. You might have seen these in Interstellar. This is an amazing picture of the interstellar black hole, which you can see as 3D. And this is what we always think of it as, but this is what it would actually be, because it's actually, space is 3-dimensional. It's actually 4-dimensional space, but 3-dimensional. So you would see a 3-dimensional hole. A 3-dimensional hole is a ball. And no matter which way I looked into it, it would look like a flat disk, no matter which way I did it. So there's no point when you look at a black hole from the side that you'll stop seeing it. It will still look exactly the same no matter which orientation that it's in. Now inside the black hole of Interstellar, there was this, because love transcends time. But that's not actually true. What's in a black hole? What's actually in a black hole is the singularity. The black hole actually bends space so much that nothing can get out of it. Not even light can get out of it, which is why it's called a black hole, because nothing escapes it. No lights get out, then it must be black. It's a black hole. The event horizon is the point where you cannot then escape it. Nothing can escape from the event horizon because it's too far into the hole. And at the bottom here we have our singularity. This is where everything that's gone into the black hole is concentrated. Now, at the bottom of this black hole, you might find that there is a link to another black hole, which comes out at a completely different portion of our universe. Or you might find that the conditions to make a singularity are the same conditions that formed our universe. So you may find another universe at the bottom of that black hole. So we're trying really to understand as humans what is at the bottom of a black hole, but it might be exactly the same as our universe. It might be a completely different universe with completely different physical rules. We have no idea. But black holes are incredibly interesting. Go and find out more on anywhere you like. Okay.